So we left off going over Peterson olefination examples. Cool, right? So we had talked about this example here, right? The hydrogens on this carbon are slightly more acidic because they're beside an alkyne, and they're a little bit easier to get to since the other side, the other groups are all isopropyl. They do the addition. They do it under basic, and then they do the Peterson elimination step under basic conditions. So they basically are doing the addition followed by the elimination all in one step. They're not like isolating the alcohol. And so they got a 6-to-1 ratio of Z to E, which tells us since they didn't have to separate out the two alcohols, the addition to the aldehyde must have been roughly a 6-to-1 ratio of diastereomers. So, right, just because I am hopefully still recording. I am good. Okay. So I don't know if I wrote this before, but we know we have, just because we have a 6-to-1 ratio, right? We know we have a 6-to-1 ratio of this. Find it. We're gonna just cut stuff off here. Of this versus this. Right, so we know we have that ratio of addition products. It's not an alcohol, make it O minus. Right, so they didn't have to try to separate out these two isomers. They knew they had enough of their major product that they could just do it all in one step. Now, what I left off on, right, was at this point, they have to turn this alcohol into a chloride, right? So they have this siloprotected ether, so this OTBS. They treat that with TBAF, which removes the TBS group from here, and removes the triisopropyl the TIPS group, from this carbon, which gives us the terminal alkyne that we want, and gives us this alcohol. Right, but they have to turn that alcohol into a chloride. And they do that with carbon tetrachloride and N-octyl phosphine. And I wanted to show how that works because it's kind of a variation on a reaction that gets used relatively frequently. So I wanted to kind of just show how that worked real quick. So basically they're taking, so I can sit down, huh? Sit down. There we go. So they're taking an alcohol and they're turning it into a chloride, and they're inverting the stereochemistry. So what's the first thing you should think about? You're inverting your stereochemistry. What reaction should you think of if you invert your stereochemistry? It's organic 1. It was a simpler time. Yeah, SN2 invert stereochemistry. Right. So they have to turn this alcohol, needs to be a leaving group. So they need to turn that alcohol into a leaving group. So they're using carbon tetrachloride, and I'm just going to put R3 phenyl. Not phenyl, phosphine. So them picking N-octyl was probably just like a what's the word I'm looking for? Trial and error. They probably tried a bunch of different phosphines before they got to N-octyl as the best one. Now this is going to work similar to the Corey-Fuchs reaction in terms of how this works. So if you remember the Corey-Fuchs reaction, Corey-Fuchs, right? You had your phosphine, and it reacted with a carbon that had 4 halides on it, and the phosphine added to one of the halides and pushed electrons onto the carbon, right? So the carbon was actually the leaving group in this case because you've got all these electron withdrawing groups around the carbon. So the carbon has electrons pulled away from it. So it wants to have electrons, right? It's short electrons because there's all these chlorines around it pulling electrons away. So it's able to actually become a carbanion to make up for the fact that it's losing electrons to these halides. Now in the Corey-Fuchs reaction, the carbanion adds to the phosphorus, right? But here, I've got an alcohol present in my molecule. So instead of my carbanion adding to my phosphorus, my carbanion is going to act as a base, and it's going to grab this hydrogen, kick electrons onto the oxygen, and I'm going to have a negatively charged oxygen, and I'm going to, if I can write correctly, make chloroform. So HCCl3 is chloroform. Now my alkoxide can add to the phosphorus and kick off the chlorine. And so now you're going to have turned your oxygen into a good leaving group because you're going to have on it PR3 plus, and you made Cl minus in the course of doing that step, right? So I replaced the chlorine on the phosphorus with an oxygen. If you remember, phosphorus really likes making bonds to oxygen. So now that phosphorus is on that oxygen, it's stuck. We're not going to break that phosphorus-oxygen bond. But now, that Cl minus, that can be a nucleophile. I now have a leaving group over here that I made by turning my oxygen by making that bond to my phosphorus. So now I have a leaving group, and I have a nucleophile. I'm set up to do an SN2 reaction. So now this chloride can add to that carbon, push electrons up, and that's going to make your chloride. It's going to invert your stereochemistry, and you're going to make still not that. 15th times the charm. There you go. Plus, minus, right? And this is basically just a resonance structure of the phosphorus-oxygen double bond. Oh, why is it sitting there? 1 second, let me fix it. I'm sorry, I didn't realize it was there. Let me see if I can move this down. Problem is I have a hard time doing stuff with it on the other. 1 second. Old man fights with technology. Recording box, go away. There, stop it. There you go. If I don't mess with it, it's good. Sorry about that. Do you need to go back to the other slide to, move the big recording box out of the way? Okay, sure. Sorry about that. No, stop. Okay, I gotta get over here. Okay, cool. So that was a way. Right, so we learned a bunch of different ways to turn oxygens into halides, but this is another one that's kind of does something similar to the beginning of the Corey-Fuchs reaction. So like the synergy, everything's coming together here. Seem reasonable, everyone? All right, so back to the slides. Okay, and then so that got them the product they wanted, right? And so you could think that you don't want to put anything in here that makes like HCl or anything that's going to be strongly acidic because you've got all these double bonds and this alkyne, right? So you got to be careful about how you turn your OH into a halide because anything too harsh is going to start messing with those double bonds. You're going to start adding a hydrogen, adding a halide, and so you've got to be careful about how you do it. So this last example is just one where they actually put an electron withdrawing group on the alpha carbon by the silicon, so they can make this hydrogen more acidic than the hydrogens on the silicon. So they are selecting for deprotonating this carbon because that carbon is beside an electron withdrawing group. In this case, it's beside an ester. And then it does the addition, and they make this isomer selectively. So next up is the Tebbe olefination. Teletubby. No? Teletubby? Yeah, Teletubby. Tebbe. Tebbe olefination. Teletubbies are well before my time. I just had Sesame Street. That's all I had. Sesame Street and Mr. Rogers. I mean, everyone did, but now Sesame Street's only on HBO Max, and so I'm gonna like in 20 years I'm gonna have a bunch of like students in organic that I'm gonna be like, the Count, and then you're like, no, I didn't watch Sesame Street. We didn't have HBO in my house, and I'm like, oh my god, that is super sad. So Tebbe olefination is you use a titanium reagent, and it turns you make this titanium like carbene. So a carbon double bonded to a metal is usually a carbene. And it will turn a ketone, an aldehyde, an ester, an amide, basically any carbonyl, into a carbon-carbon double bond. So you'll just replace the oxygen of that carbonyl with a carbon. So we've seen this a few times, right? But no box. Okay, cool. So this is the thing that actually is the business part of this. Oops. Is CP2 titanium double bond to a carbon. And we saw the CP thing on Schwarz's reagent, that zirconium thing that we had in the panic synthesis of discodermalide. And I didn't tell you what CP was. And CP is a really common ligand for metals. So CP is cyclopentyl dienyl. So it's a cyclopentane, a cyclopentane cyclopentadiene, there we go, words, I teach how to name things. A cyclopentadiene that you deprotonate the carbon between the two double bonds, and then you just end up with an aromatic where you get an aromatic ion. And so that negative charge that's on that pi system just sticks to the metal. So it's a really common ligand for metals. So we've seen it a couple times now. I just wanted to let you know that's what CP is cyclopentadienyl. Where's my screen paused? Thank you. So there are two ways that you can kind of get to this titanium structure. Like this is what actually does the reaction, is the CP to titanium double bonded to the carbon. So you have this is a TEBI reagent. This is super not stable. It's hard to handle. This is one of those like has to be in a glove box thing. And then Patasis developed a reagent where you just have two methyls on your titanium. When you heat it, you generate methane gas and make the double bond. So this is a more stable reagent. This is more bench stable and easier to work with than this. But you get to the exact same thing, right, regardless of how you get there. And once you get to this is the reagent that actually does the reaction. So it doesn't matter how you get there, as long as you get to that reagent. So I have a couple little examples here where they can take this ketone, turn it into a double bond. They can take this ester and do the same thing. Right? You could probably do this first reaction with a Wittig reagent. Right? It might take a little while because it's a ketone, but you can probably do it with a Wittig reagent. You couldn't do this where you have the carbonyl of an ester with a Wittig reagent. That wouldn't work. Right? The Wittig reagent isn't reactive enough to react with an ester. So this gives you a way to turn the carbonyls of esters into double bonds. And I have a neat example of using this. Is this the one or is it the next one? It might be the next one. So I kind of go through a big chunk of the synthesis, partially to remind you of some stuff you already know. And to kind of introduce some other concepts. So this first step, step one here, what kind of reaction is that? Organic 2 Wakefield taught you this. He remembers. We were even in person. I have something that has two double bonds. I have something with one double bond. And I heat it up, and I make a 6-membered ring with one double bond. What could that possibly be? Begins with a D. Diaz autoreaction. Yay, Diaz autoreaction. Cool. All right. So this is a diene, right? And it has two electron donating groups on it, right? It's got this oxygen here. This is basically ether, right? This activating this carbon. This nitrogen is activating this carbon. So you're going to make a bond between this carbon here and that one there, right? And since these two groups, the ester and the methyl group, they're trans on the double bond, right? They end up trans on the product. Look at that. Now, right here, we've got this chiral group on the nitrogen, and that chiral group on the nitrogen is called a chiral auxiliary. It's a group that you put on a molecule that lets you impart chirality to the product, and then you take it off later. So it's not something you plan on keeping in your molecule. It's something that you use to make sure that you make the right enantiomer of your product. Right? we could predict this diastereomer. No problem. We could predict that would be the diastereomer that we would get. But we wouldn't be able to, we'd always get a racemic mixture, unless we had chirality on one of our components, our diene or our dienophile to start with. So we put chirality on there in the form of this auxiliary. We do the Diaz autoreaction, and then eventually we take off this chiral group, and we're just left with the 6-membered ring with these 2 stereocenters that we need. So the next step is, so this step 1 on the next thing is we turn this alcohol into this ether, to a benzyl ether. And then step 2, we add HF. So HF removes silyl groups, but it's also acidic. So basically what we're doing is we're putting a proton on this nitrogen and making it a leaving group, and then removing this TBS group so you can remove that nitrogen. So let me show you how that works. So they add HF. You end up protonating. You remove your silicon, and you end up protonating your nitrogen. Again, we've made a good leaving group. These electrons can come down over and push out the nitrogen, right? So we end up with an enone, right? Enones are more stable than enols. Right? Remember we said that if you had an enol, it would always turn into the carbonyl structure, because the C double bond O is more stable than having a carbon-carbon double bond with a carbon-oxygen single bond. This, I get to make 2 double bonds, right? I get to make this double bond here for the C double bond O, and I get to make this double bond. And then they're conjugated. So all in all, this is more stable than this structure or this one. All right, so this is going to make it so I add a little bit of acid, I take off the silicon group, and then that will fall apart. And make the enone. So anytime you want to make an enolate or make an enol, I'm going to change if someone yells at me. It doesn't have to be in a 6-membered ring. But if you have a carbonyl and you have anything that can be a little bit of a leaving group here, like a halide, even like something like an ether, right? If you treat this with base and try to make this enolate, what will happen is you always do this elimination to make the enone. So you can't ever make an enolate with a beta leaving group, right? So you've got, remember, alpha, beta for your carbonyl, for your carbons on your carbonyls. That's from when we were like in the end times. So like if you don't remember that, I totally understand, because you were just watching videos, right? So you have alpha, then beta. So if you have a leaving group on your beta carbon and you try to make an enolate, it always will spit that leaving group out and make an enone. So we have something very similar. We set it up that we end up making an enol with a leaving group at the beta carbon, and then it will give you that enone that they need. So they use that chiral auxiliary to introduce chirality, to make sure that they have the right enantiomer of their product. And then they also used it to be the leaving group for them to make the enone that they needed to have at the end. So they kind of got double duty. Oops, sorry that went away. They kind of got double duty out of this group, right? It made sure that these were the right RNS designation, and then it was also the leaving group to make their ENOD. And then we do a whole bunch of stuff, and we get here. So this isn't a TEBI reaction yet, right? So they do the same thing we've seen a few other times. They have one acetal, right? They have this dimethyl acetal here, and they have, it's not quite a diol, right? You have an acid and an alcohol, but they're able to use some Lewis acids, TMS triplet, and turn this acetal into a carbonyl again, and then add this oxygen and the oxygen from the acid to make this 6-membered ring. And then they do a TEBI reaction to turn this carbonyl into this double bond. And the reason I picked this is twofold. One, I used to play pickup basketball with this guy, with Todd. And two, probably more important, is this step right from here to here. Well, it's not a TEBI olefination. I thought it was just a neat reaction. And so I wanted to take a chance to talk about this and show you how this works. So you've got your carbonyl, you turn into a double bond. Then you treat it with dimethyl aluminum chloride. And you lose this kind of acetal right here, right? And I end up just making a 6-membered ring that has one oxygen in it. So what happens from here to here, right? So we're not going to draw out the whole molecule because, like, but, right, so they have this. We'll draw, like, the abridged version. So they have that, and they add aluminum with, they have 2 methyls and a chlorine, but just about any aluminum will work. Aluminum is I'll make a different color. This is a Lewis acid, meaning that it will accept lone pairs from stuff, right? So I can take the lone pair from this oxygen, and it will donate those lone pairs to the aluminum. Now this kind of looks like when an acetal falls apart, right? One of the oxygens gets a positive charge, and then the other oxygen can push electrons down and onto the other oxygen. So this is going to make so this is effectively an enolate, right? Right, if I were to break that oxygen off the metal, right, the oxygen would have a negative charge. So this is like an enolate. And now I have basically a nucleophile in my molecule, and I have an electrophile in my molecule. So if I rotate this around, curly Q arrow, now I'm set up 1, 2, 3, 4, 5, 6 for the, let me move this real quick. The electrons in this aluminum oxygen bond can come down, push these electrons over and onto that oxygen, and that's going to make the 6-membered ring that you see. So that's going to lead to that as your product. So if I were to number, let's go back. So it's 1, 2, 3, 4, 5, 6. So they're able to open up that ring that they made, have it be an enolate, then have it add to the oxonium ion, the carbon double bond to an oxygen, and the oxygen having a positive charge, to make the ring that they needed to make to get through to the final product. Did everyone get that? Did I go too fast? I hope I didn't go too fast. Right, so they went from here to here. And I didn't go through and draw out the actual transition state, but they were able to get the correct stereochemistry that they needed for this carbon when they did the reaction. And they did more steps than they got here. Okay. So, the too long didn't read. Right? There are a lot of ways to make double bonds from carbonyls. Right? We've got just keeps hitting his head on this stupid thing. We've got 5 or 6 more methods to do that now. Right? You can select for the E or Z that you need for your double bond, oftentimes just by the choice of reagent. So you can pick the right reagent, and that's going to give you mostly E or mostly Z, and it's important to know which reagents do which thing, right? To be able to say oh, that reagent, that reaction makes the trans double bond all the time. Oh, this other reaction makes the cis. I need to make the cis double bond. I need to use this reagent over here, right? So that selectivity comes from the mechanism, understanding how the mechanism works, understanding the choice of reagent, and how base and stuff can impact that. Right. But sometimes the substrate that you're doing the reaction on might try to overrule the reagent selectivity, and that's why even though I only showed you a few examples, there's a lot of different variations of solvent, temperature, and additives and base that all these reactions go through, because sometimes you've got to try to coax or tune your reaction to do what you want it to do. So what I wanted to do, see if I have it up here. I know we're not sharing a screen right now. I understand Zoom. They're just looking at a big version of me. I know it's rough. So I didn't forget. I was going to send this to you guys, but I decided not to. See here, open. Okay. So here's what I'm thinking we're going to do as kind of a review, kind of a bit of a refresher, right? So I think it's going to be easier for me to just draw these as opposed to putting up a slide. How would you make that? Just going from benzaldehyde to that trans double bond. Well, I mean, you could look through stuff. We're gonna talk it out here. people of various modalities of learning. How many people do I have today? But I've got, oh, we've got like everyone. I think, yes, we have everyone. Okay. So how would you make that? So we need a way to make a trans double bond, and we need it to have a carbonyl on it as well. I'm going to give 2 ways that you guys know how to do this. Excellent. This is using so much time. I didn't need more slides. I have to ask you guys to do stuff. Excellent. Wait, you have a new notebook for Advanced Organic? You ran out of space? Good job, me. Come on. So how would you do this? People of Zoom, you're allowed to participate. So what are the ways that you know how to make trans double bonds and like have a carbonyl in your product? This is Advanced Organic. Like this is stuff we went over this semester. Like in the last like week and a half, 2 weeks. I promise you. You do have that notebook with you. Yeah, okay. Man, I'm gonna get to burn 36 minutes on just asking one question. I made 1, 2, 3, 4, 5, 6, 7, 8 of these. All from benzaldehyde. We could. So we could do a Horner-Wesson Emmons. So like the classic thermodynamic version. So what is the difference between what is the thing about the Horner-Wesson Emmons when it goes through the thermodynamic pathway? What is the thing that's normally you make that decision by what's on the phosphorus? What's normally on the phosphorus for that reaction? What should be over here? And it's an ester, but so it's usually F-oxy, right? So basically, there's no fluorines here. That's all right. It's fine, right? So when you do a Horner-Wesson Emmons to make a trans double bond, you use the reagent that has an ester, and we're going to pick a base. So it'd be something like sodium HMDS kind of deal. All right. So you'd use a Horner-Wesson Emmons that doesn't have the fluorines on it, right? The fluorines make the cis double bond. They're not the fluorines make the trans double bond. What's another way? There's so much rattling around in your heads now. I'll keep it organized. So the other way is a variant of a Wittig reaction. So you'd use a Wittig reagent, you'd use a stabilized ylide. right? So you'd use an ylide that had a carbonyl group on it that helps stabilize that ylide, and those reagents are the stabilized ylides for a Wittig reaction. They prefer to make trans double bonds. So these are two ways that you know how to make a trans double bond in one step that has a carbonyl group on the end. Now, same thing. Let's. Oh no, you can actually draw it. It's fine. I'm not in a big hurry. We'll go through we'll see how far we get. We'll make you guys all think. Because I know I haven't done a bunch of examples because I've been trying to do like actual real life examples because it's hard to like make up examples as things get more complicated. But I think it's good to make you guys like think about all the stuff we've gone over as of late. So it's not just all like gobbledygook in your head. I already started making your exam, so that's good. I wanted to make an example for a slide, and I started drawing it. I was like, this would make a really good test question. I should just make this a test question. So it became a test question. It's all good. Okay. What about this? Taking benzaldehyde. And making a trans double bond. How would you know how to do that? So no carbonyl this time. So Hortowatz amides and stabilized Wittig reagents are out. But how could you make a trans double bond out of this? I'm gonna turn the tables. I'm making you guys think now. Oh no, it's horrible. Oh, side note, do you believe the SciFinder assignment's due today? I think. Sure, due by midnight. Sometime tomorrow, I will just type in like homework assignment 2 into my email, and then hopefully everyone's subject line comes up, and I can just like download their assignments and then grade them real quick. Alphonse has unmuted himself. He's feeling confident. We could do it with a Julia olefination. So what do we need to do a Julia olefination? Let's assume we're gonna do the classic Julia. So that takes 3 things, right? So we need 3 things to do a classic Julia olefination. So first we need the sulfone, right? So this has 1, 2, 3, 4, 5 carbons, right? So you're gonna have 1, 2, 3, 4, 5 carbons. That's gonna be bonded to the sulfur. And in a classic Julia olefination, that sulfur is usually just on attached to a phenyl group, and we have 2 oxygens. Right? And again, we're going to need a base. They usually use an HMDS, a hexamethyl disilazine. Right? So that first step, that's going to add this carbon right here to this carbon. So we're going to get something that looks like this. So upside down, 1, 2, 3, 4, 5. Wait, no, one too many carbons. Those are the first time. 1, 2, 3, 4, 5. So the methyl group is here. So that's what we get after step 1. So what do we need to do for step 2? Did you say acid chloride? Yeah, you need to add an acid chloride or an anhydride or something. You need to turn your oxygen into an acetate. Right? You need to turn your oxygen into a leaving group of some sort. So then step 2, so this is 1. Step 2 is the same thing, except for now your oxygen is a leaving group. And then what is the third step? What do we have to do for the third step? We have to do a reduction. So there's two main conditions for reduction that we use, right? One is sodium and mercury, usually with methanol, because that lets us make a base as well. And that will remove the acetate and then remove the sulfone to give the product. What's another way we can do this? It took a lot to get Julia olefination out of you, and then he asked for a second thing. What a bad man. So we're all out of sulfones. What's another way we can do this? We just talked about it. We just talked about versions of it today. Oh, that's a really bad pH. It's a really bad phenyl. Yep, really bad phenyl. I just made it worse. pH. Right, so this is step 2, and then the end of step 3 is actually the product. Right, another thing we could try to do, right, is we could try to do a Peterson olefination. Right, so if we did a Peterson olefination, what would we need to have? We have our benzaldehyde. Right, a Peterson olefination, we need a silicon with 1, 2, 3, 4, 5. Right, so this carbon right here is the carbon on the silicon. Right. Usually they have some big group on the silicon. Usually they use isopropyl. Right, so it makes it hard to get to those carbons on the hydrogens on the carbons on this on these groups here. So then the most acidic hydrogen is this one here. So then you'd also need to take this and base. So usually like N-butyllithium. That's step 1. And after step 1, you're going to get a mixture of this plus, oh, negative aromatic. don't know what's wrong with me right now. Plus this. Now, one of these, A or B, I would treat with a base to make the trans double bond, and the other one I would treat with acid. Which one gets treated with acid to make a trans double bond? So B, the two groups are already on opposite sides. So the way I have it drawn, I would treat this with base, something like KH. Because what that does, right, is it makes the oxygen negative and has the oxygen add to the silicon. Right, so the way I have it drawn right now, if I have the oxygen bond to the silicon, when that falls apart, my two groups are on opposite sides to start with. They're going to stay on opposite sides when I make the double bond. Here, my two groups are on the same side. So to make them go on opposite sides, I treat this with acid, and that causes, right, I'm going to go over a slide. Hopefully you guys get that drawn. Right, so I've got this. I just to make the R so I have to draw the whole thing. Here they're on the same side. When I add acid, right, the mechanism is I protonate the alcohol. And then for the elimination to occur, I have to rotate around the single bond and put the silicon on the opposite side of the molecule from the oxygen. And when I do that, now my carbon chain and my benzene ring are on opposite sides. So when this does the elimination, I end up making the trans double bond. So the diastereomer that you make, you can pick which conditions you use depending on which diastereomer. Reasonable. Look at all this fun stuff you guys know now. All right. How can I make that? This could, in fact, be Jonah's time to shine. So we went over a couple of things, one in particular that we kind of talked about already, that makes cis double bonds selectively. Oh, there's a message in chat. Oh no. Jonah from 1003 was also correct about this. So Jonah from 1003 said we should use the thermodynamic version of Horner-Rosen's. This is the kinetic version, right? This is where you change the carbon group on the phosphorus. So instead of having just carbons, right, and hydrogens, this is the version where you do CF3, CH2O. Okay, this is the Stoljari variant, where this group, having the fluorines on here, selects for the cis double bond. Right, you want to make the cis double bond here, and then again, you're going to use a base like potassium hydride or KHMDS. Right, so just changing basically 3 hydrogens to 3 fluorines changes the Horner-Rosen's reaction from being trans-selective to being cis-selective. Okay, so I've got more of these to do.